Experiment for demonstration of equilibrium condition. So how you can demonstrate that body is in equilibrium? Here basically we have to show the second condition of equilibrium, that the total clockwise movement is equals to the total anti-clockwise movement. So first of all, see this figure. In this figure you can see four forces are acting here: F1, F2, F3 and F4. First of all, you have to set up the apparatus as shown in this figure, and you can see on the beam four forces are acting at different position. When you have to find out the magnitude of these forces, actually here is a Newton meter. This Newton meter is basically used to find out the magnitude of the forces. After that, you also have to find out the distance of each of these forces from the end of the ruler. Just consider that the pivot point is here on the right side. Calculate the distance of all of these forces from this pivot point. After that, calculating the distance from the pivot point, you have to calculate the moment, because you know that moment is the product of the force that you calculate with the help of Newton meter multiply by the distance d. This distance is the distance of these forces from the pivot point. In this way, you can calculate the moment of all of these forces about the end of the ruler. Then you have to realize here that which force causes the clockwise movement and which force causes the anti-clockwise movement. Accordingly, you have to find out the total clockwise movement and the total anti-clockwise movement. Then use here the conservation of moment. The total clockwise movement must be equals to the total anti-clockwise movement. By using this, at the end, when you find out the total sum of the moment, it would be equals to 0. When the total moment is equals to 0, this condition is basically for a body to be in equilibrium, which is the second condition. So I can simply say that when the net moment is equals to 0, the body is in equilibrium. So let's go back and see these steps. First of all, set up the apparatus as shown in the figure. Different forces are acting on the beam, and the magnitude of these forces can be determined by taking the reading from the Newton meters. You have to take the reading from the Newton meters. These are basically the value of the forces. Measure the distance from each force and the end of the ruler. Calculate the moment of each force about the end of the ruler. First of all, you have to find out the magnitude of the forces. Then measure the distance and at the end calculate the moment of all of these forces. Then add up all the clockwise and anti-clockwise moments separately. In the figure that is given below, the clockwise moment is caused by the force F2 and F3. Second force and the third force causes the clockwise moment, whereas the anti-clockwise moment is caused by the force F1 and F4. Finally, you will notice that the total sum of all the moment is equals to 0. When the total sum of the moment is equals to 0, this is basically the second condition of equilibrium, that the resultant moment acting on the object must be 0. Therefore, we can conclude that when the body is in equilibrium, there is no resultant movement acting on the object. So in this way, you can demonstrate the second condition of equilibrium, that the net moment must be equals to 0. That's the simulation related with the equilibrium condition as well as with the law of conservation of the moment. Let's open this. First of all, I will open the intro. Here you can see that there is a beam and there is also the pivot point. First of all, here you can see positions. You can mark the ruler as well as you can mark here only marks, which shows the point 1 to 3 on both sides of the pivot. You can use any one of these. If you don't use them, then you click on none. So first of all, I suppose there is a 5 kilogram mass. It is placed here. Here you need to see the marks. Let's see, it is placed at 4. The second object whose mass is 10 kilogram is placed at 2. Let's see this. Here you can see the moment caused by both of these objects would be equals to 0. If I display the second object on the other side, you can see here the moment is not equal. Like here. One side moment is larger than the other side moment. So for a body to be in equilibrium, the moment would be equals to 0. It means that here the mass is 10 kilogram and you place it at the second point. While this mass is 5 kilogram and you place it at 4 point. It means that in this case both of these moments are equal. That's why this beam is balanced. It's not moving. When the beam is not balanced, of course it will move on one side depending upon the value of the moment, which moment is larger than the other. Let's go to the second balance lab. Here is again the different bricks and the masses of all of these are given. First of all, I set here marks and forces from the object. I suppose there is a mass of 20 kilogram placed at 3. And the second is 10 kilogram placed at 6. When I open this, you can see both of these moments are equal. So when both of these moments are equal, it means that this is balanced. Now if I move the second mass on any other side just at 7, you can see here this beam is not balanced. It is moving. So in this way, you can simply say that when both of these moments are equal, the beam is balanced. The net moment must be equals to 0 in this case. But here it's moving on the right side. It means that it's not in equilibrium. Like here, the second condition of the equilibrium is not satisfied. The total moment is not equals to 0. You can also use here the ruler as well and set the values again. In this way, both of these are balanced. That's the second condition of equilibrium, that the clockwise moment must be equals to the anti-clockwise moment. When both of these moments are equal, the body is in equilibrium because the total moment is equals to 0. Because the total moment is equals to 0. You can practice it here. Let's go back.